Hello everyone and welcome to today's video illustration where I'll be showcasing an AI written in Python that will assess the likelihood that a person in a specified family shows a particular genetic trait. Specifically, we're going to be focusing on the gene GJP2, which is one of the leading causes for hearing impairment in newborns. Each person carries two copies of that gene or two versions of that gene, one passed down from one from the mother and the other is from the father, and then we want to assess the likelihood that that person will have one, two, or no copies that might show symptoms or traits that will cause hearing impairment. And our final output will be something like this, where we state the person's name and then the gene and the likelihood the probability for having a specified number of copies, and then based on those copies we want to calculate whether they will show the specified trait. In this case is the hearing impairment. And we'll think of this as a Bayesian network, since the child inherits from his mother and father, and the probability that we have any number of specified copies that might show the trait is dependent on both his mother and father. So we'll represent it in this Bayesian network. As for the mother and father, the probability will be fixed for each copy. And in our code here, if you jump to the top, the fixed probability is as shown here, and the fixed probability of each trait based on the number of copies is this. And what we'll do here is, first we're going to return a list of all of the possible subsets that we can have, and then for each subset we're going to calculate the joint probability. So for example, the probability that, if I go back here, the probability that Harry, for example, has no copies or shows no copies, James shows one copy, and Lily shows two, and Harry will return true for trade, James will return false, and Lily will return false as well. And we'll calculate that joint probability, and then using the update function, we're going to update our probability distribution, adding P, where P is our joint probability, to each of the respective field. So we wanted to calculate that Harry will have 0 copies of the gene, so the joint probability will be added to Harry of 0, representing Harry having 0 copies. And finally, instead of calculating the denominator when we calculate the joint probability, since it tends to get complicated, we'll just ignore it, and then using the normalize function, we're going to make the set or the probability distribution equal to 1, and this will help us easily identify our denominator, which will be total in this case, 1 over total, and we'll multiply the entire thing with it. And so if you run the code here, and yep, let's start with one of our data, a family of 0 for example. We'll see that it works perfectly, and for each person it's giving us the likelihood that we have a specified number of mutated genes and then the traits. Oh, and it's obviously worth mentioning that when passing down the genes, so when a mother passes down the gene, if the mother, for example, has 2 copies of the gene, then it is guaranteed to pass down the gene that will cause this mutation, except that there is a 0.01 chance that the reverse will happen. So for example, if the mother has 2 copies of the gene that shows the trait, there is a 99% chance that it will pass it down, but a 1% chance that it won't. And likewise, if she has no copies at all, then she's more likely, with a 99% chance, that she will not give him a mutated gene, but there is a 1% chance that she would. And if she only has 1 copy of the mutated gene, then it's a 50-50. And that's our output here. And if we run this again, well, using family of 1, we'll see that the file this time is bigger, but likewise we generated the probability for having each number of traits. We see here that for Arthur is more likely to have no copies at all, therefore it is almost guaranteed that he will not show any symptoms. Likewise with Charlie and so on. And then as we can see, we can evaluate it, and the closer they get, the more disturbed the probability of showing a trait will be. And lastly, let's show family of 2 or family 2. And again, we basically calculate the probability for each gene, and then based on the gene, calculate the probability for the trait through our joint probability as explained before. That's all. Thank you so much for watching, and have a nice day.